Assalamualaikum and selamat sejahtera. In the previous video, I have introduced three types of DC-DC converters. As mentioned, the input DC voltage can be stepped down or stepped up using the buck and boost converters respectively. Meanwhile, the buck-boost converter can perform both functions depending on the duty cycle or duty ratio. In this video, I will show you how to derive the output voltage equations of these converters. For your information, the most essential parameter used in the derivation is the instantaneous inductor current. Before we analyze the inductor current, we need to consider one assumption. Due to the large inductive size, we assume the inductor current is always continuous. Therefore, the DC-DC converters will work in a continuous conduction mode, or also known as CCM. For this simulation work, I choose to simulate the buck converter circuit. Throughout the simulation, I will measure the input voltage, control pulse, inductor current, output voltage, and output current. When I zoom the steady-state waveforms, we can see the output voltage of the converter is lower than the input voltage. Hence, the buck converter has successfully stepped down the input DC voltage. Other than that, we can see the output voltage and output current have continuous waveforms with constant amplitude and ripple free. At the same time, we can see the inductor current also has a continuous and ripple free waveform. However, when I zoom further, we can see the wave shape of the inductor current is actually zigzag. From the graph, we can see the inductor current increases linearly when the control pulse is applied to the IGBT. Meanwhile, when the control pulse equals to 0, the inductor current decreases linearly. Next, I will explain why the inductor current has this kind of wave shape. This figure shows a complete cycle of the inductor current waveform. The period, turn on time, and turn off time can be written as follows. According to the duty cycle equation, we can write the turn on time equals to dt and the turn off time equals to 1 minus d times the period. Based on the turn on time equation, we can label the x-axis like this. Next, we will analyze the characteristics of the inductor current when the controllable switch S1 is in on state and off state. When S1 is turned on, it is also known as S1 is closed. At this moment, the inductor is energizing and it causes the inductor current increases linearly. Hence, the current has a positive gradient or a positive slope. In this condition, the inductor is energizing to store magnetic field. Meanwhile, when S1 is turned off or S1 open, the inductor is de-energizing. As a result, the inductor current decreases linearly and therefore the current has a negative gradient. In this condition, the inductor is de-energizing to supply current into the circuit. Next, we will focus on these two differential equations. We can replace these equations as follows. Delta IL represents the change of inductor current, while delta T is the change of time. In overall, delta IL over delta T is representing the change of inductor current towards the change of time. When S1 is turned on, delta T is equal to the turn on time, which is dt. And when S1 is turned off, delta T is equal to the turn off time, which is 1 minus d times t. Eventually, we will complete the analysis by considering another assumption. Under the steady-state operation, we assume the change of inductor current during S1 closed is equal to the change of inductor current when S1 open. From the graph, the change of inductor current is also known as the peak-to-peak inductor current or the ripple of inductor current, and it can be calculated using this equation. This flowchart shows all procedures to derive the output voltage equation. In this video, I will show the derivation of the output voltage of a buck converter only. After watching this video, you must try to derive the output voltage of boost and buck boost converters using the same procedures. Firstly, we need to sketch the equivalent circuit of the converter when S1 turn on and turn off. To turn on the switch, we need to apply a control pulse between 0 until dt. And when S1 turn on, automatically D is turned off due to the reverse bias condition. Hence, we can have this equivalent circuit. Next, we need to apply KVL to obtain a voltage equation, and based on the positive slope, we need to rearrange the equation so that we can obtain the equation of the change of inductor current. From this circuit analysis, equation 1 represents the change of inductor current equation when S1 is turned on. Now, we will repeat the same procedures to obtain the equation of the change of inductor current when S1 is turned off. This time, diode D is turned on due to the forward bias. By applying KVL and rearrange the voltage equation, eventually we can have these following equations. Lastly, we need to solve these two equations based on the previous assumption to obtain the output voltage equation. According to this derivation, the output voltage of the buck converter is equal to Vs times the duty cycle.